Welcome to section 3.8, Related Rates. Let's begin with an example. Example 1. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So you've got this balloon and air is being pumped into it at a certain rate. It's 100 cubic centimeters per second. So here is the sphere that's looking like where there's your the diagram, I guess. So what we see here is a related rates problem because it's asking for the rate of change of the radius as it relates to the volume as the volume increases. And naturally, we will have to use the equation of the volume of this sphere, which is 4/3 pi r cubed. So let's go ahead and solve this problem. Now notice that there are a few things that we have to look at in this problem. For example, it talks about how fast. So this one where it says the volume increases at a rate, that's a keyword right there. And then how fast is the radius increasing, another keyword. And then when. When means when the diameter, that means it's the instant when the diameter is 50 centimeters, which means when the radius is 25, because you know the diameter is twice the radius. So let's solve this problem. Right, so let V be the volume, R is the radius. We use the equation volume of a sphere, and then this is what's given, dV by dt. So we use this notation to denote the rate at which the air is being pumped into the sphere. Okay, so 100 cubic centimeters per second. So the question is we are to find dr by dt at the instant when the diameter is 50 centimeters, which means when the radius is, so when r is 25 centimeters. So what do we use? We use the equation 4/3 pi r cubed. We differentiate both sides with respect to WRT, means with respect to time t. Because remember, the volume and the radius are changing or are functions of time because they both change with respect to time. So they are both functions of time. All right, so let's go ahead and differentiate. So when we do that, let's go ahead and do our differentiation right here. All right, so now we go what's the derivative with respect to time of v? dv by dt, which is equal to 4/3 pi is a constant, so all we have to do is differentiate r cubed. So the derivative of r cubed with respect to time is dr squared multiplied by dr by dt, chain rule. Because this part is only the derivative of r with respect to r. Okay, the derivative of r cubed with respect to r. So now, after we've differentiated, it's time to substitute the given. So we substitute dv equal to 100 here, and then when r is equal to 25 right there. So let's cancel that. This becomes 100 cubic centimeters equal to 4 pi, and then multiplied by 25 squared dr by dt. Remember, that is the unknown. That is what we want to find. So we need to solve for this quantity. So moving everything to the right, to the coefficients to the left side, we see that dr by dt equals 100 divided by 4 pi 25 squared. And the rest here is just this cancels out, and one of the 25 is left. So this is now equal to, so dr by dt is finally equal to 1 over 25 pi, that's 25 pi centimeters per second. Right, so how did the centimeters per second come about? This is a cubic centimeters. This is a squared centimeters, so 1 unit of centimeters left, and there's still that per second, so that's the per second right there. So this is now dr by dt, and this solves the problem, and it answers the question of how fast the radius is increasing. And notice that we only substituted after we differentiated. That's the only time we substitute the given, okay, at the instant. So that's when we have that in why this is a very important word. Okay, so let's see what were the steps we did to solve this problem. So related rates strategy, related rates problem strategy. It says draw, okay, so we're supposed to draw a picture and name the variables like we did. We let v be the volume, r be the radius, use t as time, okay, and all of them are differentiable with respect to time, and functions of time, rather, differentiable functions of time. All right, now the next thing we did was write down the numerical information. So dv by dt was given, so we use that as our rate of change of the volume, the rate of increase of the volume. Okay, and then we said what was being asked for. So it says, so here we said that we are to find dr by dt. Okay, so see, it says usually it's a rate that's being asked for, and it's expressed as a derivative. So that's a derivative of r with respect to time. Write an equation that relates the variables. So we wrote the equation 4/3 pi r cubed. And then we differentiated both sides with respect to time. Then after that, this is when we evaluated, we used all the known values to find our dr by dt. Okay, so we used this information and also the information when r was 25. So a couple of, a few things that we need to remember is that, okay, so when to substitute the given. We substituted the given after we differentiated. We only substituted the given if there are fixed, like say fixed height, fixed length, and so on, you know, those that are not changing. But when you see that the radius was changing, that the instead the diameter was 50 centimeters, then we didn't substitute the given until after differentiating. Okay, next, the given information and the unknown will hint on what equation to use. Remember, we were looking at the rate of change of volume as air is being pumped into the balloon. That tells us already that the equation we're going to use is the volume of a sphere. Now, consistency of the unit of measure is very important. So if the answer, or rather if the question is looking for rate of change of the radius, that means we should get a unit of measure of centimeters per second, not centimeters squared nor cubic centimeters per second. No, it has to be just centimeters per second, and we did attain that unit of measure. Now don't forget to convert if necessary. Say if they're asking for how, let's say feet per hours, and the quantity you got was feet per seconds, then you have to use conversion if necessary. Okay, all right, so why don't we apply these steps and these tips on the next problem. All right, so a ladder is 10 feet long, so there's that ladder that rests on a wall, a vertical wall. Here's the wall. Okay, if the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So a few things we need to remember, we need to pay attention is that, well, first of all, that's a fixed value because that's the length of the ladder. Okay, and then we have this rate and how fast, and the word when the ladder is 6 feet from the wall. So the ladder is creating a right triangle with the vertical wall and the ground. So here is our diagram. right here. So this is our right triangle. So let x be the length or the distance of the bottom of the ladder from the wall. Then let y be the length, the distance of the top of the ladder from the ground. This is fixed. That's 10 feet. So now that we've defined all our unit variables, then I think it's time to solve our problem. So first of all, what's given? Alright, so what is given? What's given is, okay, dx by dt, because that's how how this x is changing as it slides that way. Okay, so dx by dt is equal to 1 foot per second, and we are to find dy by dt. In other words, how fast this is going down from this top of the ladder as it goes down whenever this is sliding to that side, away from the wall. Okay, so let's do that. So we are given that's our x, that's y, this is fixed, so we use, and let's rewrite what's given. Dx by dt equal to 1 foot per second, and we are to find dy by dt. Okay, so what do you think is the equation we're going to use? Isn't it obvious that we're going to use the Pythagorean Theorem? Okay, so x squared plus y squared is equal to 10 squared. Then we differentiate both sides. So it's 2x, that's with respect to x, so multiplied by dx by dt, chain rule, because we are differentiating with respect to time. So plus 2y dy by dt equal to, what's the derivative of 10 squared? That's constant, so 0. So everything is divisible by 2. Let's go ahead and divide everything by 2. So you've got x dx by dt plus y dy by dt. And now that we differentiated, it's time to substitute what's given. X is given, this is given, this is the unknown. Now we need to find out what's y. Okay, so y can be found because, right, when x is equal to 6, then we can find y. Y is, right, so we say 6 squared using the Pythagorean theorem. Y squared equal to 10 squared. So y squared is equal to 100 minus 36, that's 64. So solving for y, we get y is equal to 8 by taking the square root, and we don't need to use the negative because this is a length of a measure of length. Okay, so now I think we've got everything that's taken care of. So now it's time to substitute. So now we go 6 times 1. So there's 6 times 1 foot per second plus 8 times dy by dt. So all I did is substituted everything that's equal to 0, and so dy by dt is just equal to, move the 6 to the right side, so it's minus 6, divide everything by 8, so that's equal to negative 3 over 4 of a foot per second. So this is how fast the top of the ladder is sliding down the wall. And why it's negative? Because this is sliding down as the x slides to the right. Okay, so there's the answer to the question, right?